Hey y'all, today we're going to be covering an important topic in integration, and that's the topic of U-substitution. Just like with deriving, not all functions can be handled with just an application of the power rule. And it turns out, with integration, we're going to need more techniques in order to deal with more complicated functions. So without further ado, let's get into it. So let's start with a leading question. If f of x is equal to 5x squared plus 7 all raised to the 6th power, what's f prime of x? Well, if we're exploring this, we'd say, hey, we have a function trapped by a power or trapped by another function. So in order to find f prime of x, we need to use the chain rule. The chain rule says, do the derivative of the outside, so 6 times 5x squared plus 7 to the 5th power, and times it by the derivative of the inside, which would be 10x. So ultimately simplified out, we could say that the derivative was equal to 60x times 5x squared plus 7 to the 5th power. Now, as far as our integration talking has been going lately, we've been discussing it as a way to undo a derivative. So a very fair question of me to ask would be, evaluate or find the integral of 60x times 5x squared plus 7 to the 5th power with respect to x. But if we notice this, if you look at this problem right in here, this doesn't follow any of the rules that we've talked about. It doesn't follow our integration power rule. So ideas of maybe having to multiply that in, well, maybe that could work. Or expanding this 5th power out, that could work as well. So we could use algebra to overcome this problem. However, that would be a little bit cumbersome. So we'd like a new tool or a new method to deal with this, just like we developed a new method to deal with this. So U-substitution will actually be the idea of how to undo the chain rule. So let's get into an example of how this thing works, and then we'll discuss the specifics. So let's go ahead and explore this U-sub idea by actually just trying something out first. Allow me to go ahead and show you the idea before we discuss how to do it. Compute the following integral. 60x times 5x squared plus 7, all raised to the 5th power, with respect to x. Now, I do not want to go ahead and expand this out. That would take forever, and if this power was bigger, we'd be in a lot of trouble. So allow me to do some sorcery right here. Let's let u equal 5x squared plus 7. Okay, that's not a problem. 60x times, I guess just plugging in u, we could say that's times u to the 5th power with respect to x. Well, maybe that didn't help. But maybe if I make this an integral with respect to u, i.e. I derive or I integrate u instead of x, we might be in for something. So just follow along. If I take u and derive it, well, one way to derive or to write the derivative is du over dx. That's just equal to 10x. Go one step further with me. Just by multiplying up and dividing over, du is equal to 10x times dx, or ultimately dividing over by 10x. dx is equal to 10x, or excuse me, du divided by 10x. So just doing some random algebraic manipulation, we actually arrive at something. I can plug this in for dx up here. So plugging that in for dx gives me 60x times u to the 5th times, subbing in for dx now, du divided by 10x. But wait a second. We can now cancel some things out. The x's cancel along with a good chunk of the constant. This 10 and that 60 reduced to just 6, leaving me with the integral of 6 times u to the 5th with respect to u, du. But now hold up, could we just derive or integrate this as usual? Turns out absolutely, so long as the variable matches the variable I'm integrating with respect to. So now, by our power rule, copying down the constant, add 1 to the power, and divide by the power you landed on, and then don't forget the plus c, gives me something like that. Or ultimately, canceling the constants, u to the 6 plus c. And now all we have to do, since this is actually what this is equal to, if we want our answer in terms of x, we could just sub back in. Equals 5x squared plus 7 to the 6th power plus c. And in fact, that will be our answer. This is the idea behind U-substitution. I don't like my integral as it was. So maybe I could sub in for something, let's say u equals 5x squared, and change the problem in terms of u to get an easy integral, but then I can integrate that, and then all I have to do is plug back in to get my answer in terms of x. It really is a lot like magic. Now let's get into the actual process as to how this thing works. Now let's break down what just happened in more of a process manner. So first and foremost, the cue for this. When given an integral that can't be done by your power rule, or it can't be algebraed into a power rule situation, meaning there's not simple algebra you can do to just make it a power rule. If this is your situation, here's something to try. Step 1, define something to be u. Usually this is a thing trapped by the power, by some kind of power, the power of e to the blank, so whatever that blank was, or the denominator of a fraction. Whatever it is, try to defining something to be u. Step 2, now that we've defined something to be u, we're actually committed to turning this whole integral into terms of u. Therefore, the dx will not fly. We need a du in the picture as well. So step 2 is sub in for both what you called u, as in define it to be u, and then also sub in for dx. We need a du in its place. The way we get our hands on that is actually by deriving u. Once we actually sub in for both what we called u and for dx, we can do some algebra to cancel out and make it a simple integral. Assuming now that we landed on something that can be done with the power rule, go ahead and integrate with respect to u. Get your hands on an answer that will have u in it, with the plus c of course. And then last but not least, go ahead and sub back in for u to get our answer in terms of x. Really what helps me think about this is thinking about it as a translator. We have an integral that we don't necessarily understand the language of, i.e. how to do it. It would be really nice to have a translator, which is actually what u is. U translates the problem into something we can do. From there, we can go ahead and understand the statement of it, give an answer in terms of u, the language we understand, but then, via our translator, we could convert it back into the original language in terms of x. Now let's go ahead and see another example problem where we will follow this exact process. Here's an example that will require U-sub. Integrate the following. 8x times the square root of 4x squared plus 10, all the square root of that, with respect to x dx. So, the reason it's going to require U-sub, if I look at this, the first question I always ask is, can I do a power rule to it? Well, no, I got a square root involved, right? Can't really algebra it out to make it a power rule either, without it being really cumbersome. So therefore, let's go ahead and try U-sub. The very first thing, a thing that's always handy in calculus, will be to write this square root as a 1/2 power. Now remember the process from the previous slide. Call something to be u. Usually it's the thing trapped by the power. Let's call u to be 4x squared plus 10. From here, I am committed to turning this integral into terms of u in order for this to work out. So therefore, I need a du in place of this dx. The way we get something to sub in for dx is by deriving u. So we derive u, du over dx, our notation for the derivative, and that's equal to just 8x. Since I'm trying to sub in for dx, I want to get dx equals something. So what do? I multiply up by dx, and I divide over by the 8x, giving me dx is equal to du divided by 8x. Now, we're at a very important stage where we actually have our translation. U and dx, both what we're calling u and what I can sub in for dx. So our next step, the very next equal sign, will actually be just subbing these two things in. So I integrate. The 8x I did not touch, so I am rewriting it. Times, well, we define this thing to be u, and it's still raised to the 1/2 power. U to the 1/2. Last but not least, sub in for dx with du divided by 8x. Now we arrive at a beautiful moment in the problem where we can actually cancel. The 8x is totally cancelled here for us, giving me just the integral of whatever's left over, which is just u to the 1/2 times du. That's the power of U-sub. It took a problem that I had no chance in understanding all the way to something that, hey, that's just a power rule situation, which we're totally going to apply. So by applying the power rule, meaning add 1 to the power, u to the 3/2, and divide by the power we landed on, so 1 over 3/2 just equals 2/3, and you can see that real quick. By multiplying by the reciprocal, it's 1 times 2 over 3. So there's your justification. So we get 2/3 u to the 3/2, and don't forget the plus c. From there, we need to go ahead and translate our problem back into the original language. So ultimately our answer will be 2/3 times, plug back in for u, 4x squared plus 10, all raised to the 3/2 power plus c. And that really is our final answer. Like I said earlier, I think a translation, a Rosetta Stone type allegory works out pretty well here. So, for instance, I do not understand Arabic. If someone came up to me and asked me a question in Arabic, I would need a translator in order to help. Imagine this is that question in Arabic. Well, if I know what the question is actually asking, maybe I could provide an answer. So first and foremost, here's the question in Arabic. I translate the problem to a question in English that I can understand. Well, if I know the answer to the question, like I do right here, I answer the question first and foremost in English. But then from there, it helps to go ahead and be courteous and give the answer back in Arabic. So I take this and I translate it back to the language of the original problem in terms of x. That's all that U-sub is. It's pretty fun once you get going with it, because now your whole class of variables you can do is pretty large. So let's get to more examples. Here we have another problem. Integrate 60x squared times e to the 5x cubed plus 1, all with respect to x. Yet again, I check if it's a power rule situation, or if it's any shortcut rule. Turns out it's not. So can I do some algebra to it? Well, no. The issue is I have something up here in the power. So my only other option as of right now is going to be U-sub. So with U-sub, call something to be u. Well, something trapped within a power is a great candidate. 5x cubed plus 1. Well, now I'm committed to turning the problem into something in terms of u, meaning I have to sub in for dx as well. In order to get that something, I need to derive u. That gets a dx in the picture. So the derivative of u will be 15x squared. Now ultimately, by multiplying up by dx and dividing over by 15x squared, I'll get that dx is equal to du divided by 15x squared. And right now, from this line and this line, I have my Rosetta Stone. So now I translate the problem into terms of u. I'm committed to doing that. This is equal to the integral of 60x squared. I did not touch that. So I have a 60x squared times e, well, I called the power to be u. So times e to the u. Times, we have a dx, but we're subbing in for dx with du divided by 15x squared. Now notice that these don't fully cancel out, but we still look for the cancellation that's there. For instance, the x squareds cancel, and 60 divided by 15 just gives me a 4. Meaning my integral simplifies all the way to just the integral of 4 times e to the u, all now with respect to u. And this is a problem I can integrate with our basic rules. Copy down the constant. The integral of e to the u is just itself. And then don't forget the plus c. That's our answer to this question. Now it would be polite of me to get the answer back in the original language of the problem, so last but not least, I just sub in for u. 4 times e to the 5x cubed plus 1 plus c will ultimately be our answer. Let's go ahead and try this one, except let's show what happens when you accidentally pick a wrong u. So first off, the integral is 21x squared plus 14x, all divided by x cubed plus x squared with respect to x. Now given a fraction, it's usually best to try picking the denominator. However, it's clearly a U-sub problem, and let's show what happens. I'll even write it in red to really signify it's wrong if we pick the wrong u. Let's let u equal the top. 21x squared plus 14x. Okay, well now we're committed to turning our integral into terms of u, so I need something for dx. To get that in the picture, I derive u. I get 42x plus 14. Solving for dx by multiplying up and dividing over, I get that dx is equal to du divided by 42x plus 14. And like I said, writing in red because this will be wrong. And to see why it's wrong, notice the following. Now I plug in for where I called u. U divided by, well, I didn't touch x cubed plus x squared, so that stays. And then I sub in for dx. Du divided by 42x plus 14. And notice that nothing cancels. So this could be an indicator of one of two things. Either u sub does not work, there are problems where that happens, or I picked the wrong u. And in this case, I picked the wrong u. This is definitely not a situation where I can simplify with algebra or enable or use a power rule. So therefore, we go and pick another u. Like I said, the bottom of the fraction is usually the best u to pick given a fraction. So let's let u equal x cubed plus x squared. Same exact process, now I'm committed to turning this into terms of u, so to get something to sub in for dx, I derive u. Du over dx is equal to 3x squared plus 2x. Meaning, once I multiply up and divide over, dx is equal to du divided by 3x squared plus 2x. From here, sub in. I did not touch the top part, but notice that we could write the top a little bit simpler by factoring out a 7, leaving me with 7 3x squared plus 2x. That's the top part. I did a little algebra, but I left it the same because I did not call that thing either u or dx. But now I start subbing in. I did call the bottom to be u. And subbing lastly but in for dx, I get du divided by 3x squared plus 2x, which now you can see why I'd be interested in factoring out the 7. From here, cancel, cancel. So stuff does cancel nicely, leaving me with the integral of 7 divided by u with respect to u. Now remember, this one might look a little weird, but remember you can always factor out a constant if you want, and just look at the integral of 1 over u. So 7 times the integral of 1 over u with respect to u. If we're remembering our shortcuts, what did I derive to get 1 over u? It had to be natural log of the absolute value of u plus c. So ultimately, now that we have that, we just sub back in for u and we get our answer, which will be 7 times the natural log of x cubed plus x squared plus c. So if you can't cancel like we did right there, either look to another u, which in this section will be the case, or this problem might not be a u-sub problem. So that's exactly how we handle this type of problem. As a last problem to try today, let's go ahead and consider the following. The integral of 1 over x times the natural log of x, all with respect to x. Now typically, when we do u-sub, we pick between either the thing trapped by a power, the entire denominator, or maybe the inside of a root, something along those lines, right? We usually are looking for something that when we derive it, we get a lot of cancellation out. Turns out the denominator is not a good choice on this problem. What instead would be a good choice would actually be natural log of x. And granted that we already checked, this is not a power rule situation or not something we can algebra to make a power rule situation. Now why do we want to pick u equal to the natural log of x? It turns out when we derive this thing, because now we're committed to turning it into terms of u, we get 1 over x. Notice that a 1 over x appears in the original problem. This is probably a better way to think about what you pick for u. If you can see something in the problem that's the derivative of something else in the problem, like 1 over x is the derivative of natural log of x, then this thing, what you're going to derive to get, will actually be the best u to pick more often than not. So, since du over dx equals 1 over x, we actually just cross multiply in this case, giving me, whoopsies, not equals, that dx is equal to x times du. From there, we finally have our translation. And we go ahead and plug in. This integral is equal to 1 divided by x, I didn't touch that yet, times u, all times du, or x times du. So plug in for dx with our translation. Notice now that the x's cancel, 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 and we just get the integral of 1 over u with respect to u. This is absolutely within our wheelhouse. We can do a shortcut way with this. What I derived to get 1 over u, it had to be the natural log of the absolute value of u. And don't forget the plus c. That's our answer, but last but not least, we have to sub in for u again, get it in the original language of the problem, and that will just be, it'll look funny, but it'll be the natural log of the absolute value of the natural log of x plus c, and that will be our final answer. The important thing to pick up from this problem is call your u to be something where its derivative, u's derivative, appears in the problem. And that will really be a good help for you. Hey y'all, thanks for tuning in today as we discovered another method of integration. This method of integration, U-Substitution, helps us undo the chain rule. So we're going to actually have ways of undoing most of our derivative rules, and this one tackles the chain rule. Now the way we went about it, after we checked, is this a power rule? No. Okay, well, can we algebra it out to be a power rule? No. Then we went to U-sub and we converted the entire integral into terms of u. This meant getting a du in place of a dx. From there, since the problem was simplified, we integrated via a power rule or another shortcut rule. After we integrated and got our answer in terms of u, we then converted the problem back to in terms of x. Now, helpful u's to pick out will usually be the bottom of a fraction, the inside of a power, or more generally, just something whose derivative appears in the problem. With all that being said, go ahead and try out your homework. This one might take a little bit longer, but once you get the feel of it, it will really feel like magic. So with all that being said, have a great rest of your day and enjoy!